Cordite is a family of smokeless propellants developed and produced in the United Kingdom since 1889 to replace gunpowder as a military propellant. Like gunpowder, Cordite is classified as a low explosive because of his slow burning rates and consequently low brisance. These produce a subsonic deflagration wave rather than the supersonic detonation wave produced by brisants, or high explosives. The hot gases produced by burning gunpowder or cordite generate sufficient pressure to propel a bullet or shell to its target, but not so quickly as to routinely destroy the barrel of the firearm, or gun. Cordite was used initially in the .303 British, Mark I and II, standard rifle cartridge between 1891 and 1915. Shortages of cordite in World War I led to United States developed smokeless powders being imported into the UK for use in rifle cartridges. Cordite was also used for large weapons, such as tank guns, artillery and naval guns. It has been used mainly for this purpose since the late 19th century by the UK and British Commonwealth countries. Its use was further developed before World War II, and as 2 and 3-inch diameter unrotated projectiles for launching anti-aircraft weapons. Small cordite rocket charges were also developed for ejector seats made by the Martin Baker Company. Cordite was also used in the detonation system of the Little Boy atomic bomb dropped over Hiroshima in August 1945. The term cordite generally disappeared from official publications between the wars. During World War II, double-based propellants were very widely used and there was some use of triple-based propellants by artillery. Triple-based propellants were used in post-war ammunition designs and remain in production for UK weapons. Most double-based propellants left service as World War II stocks were expended after the war. For small arms it has been replaced by other propellants, such as the improved military rifle line of extruded powder or the WC-8 44-ball propellant currently in use in the 5.56A, 45mm NATO. Production ceased in the United Kingdom, around the end of the 20th century, with the closure of the last of the World War II cordite factories, ROF by Sopton. Triple-base propellant for UK service is now manufactured in Germany. Adoption of smokeless powder by the British government, replacements for gunpowder, an explosive mixture of sulfur, charcoal and potassium nitrate, was the original gun propellant employed in firearms and fireworks. It was used from about 10th or 11th century onwards, but it had disadvantages, including the large quantity of smoke it produced. With the 19th century development of various nitro-explosives, based on the reaction of nitric acid mixtures on materials such as cellulose and glycerine, a search began for a replacement for gunpowder. Early European smokeless powders. The first smokeless powder was developed in 1865 by Major Johann F. E. Schultz of the Prussian artillery. His formulation comprised nitrolignose impregnated with saltpeter or barium nitrate. In 1882 the explosive company of Stowmarket introduced DC powder, which contained nitrocotton and nitrates of potassium and barium in a grain gelatinized by ether alcohol. It had coarser grains than other nitrocellulose powders. It proved unsuitable for rifles, but it remained in long use for shotguns and was later used for grenades and fragmentation bombs. In 1884, the French chemist Paul Vial produced a smokeless propellant that had some success. It was made out of collodion, resulting into a plastic colloidal substance which was rolled into very thin sheets, then dried and cut up into small flakes. It was immediately adopted by the French military for their MLE 1886 infantry rifle and called powder B to distinguish it from black powder. The rifle and the cartridge developed to use this powder were known generically as the 8mm Lebel, after the officer who developed its 8mm full metal jacket bullet. The following year, 1887, Alfred Nobel invented and patented a smokeless propellant he called ballastite. It was composed of 10% camphor, 45% nitroglycerine and 45% collodion. Over time the camphor tended to evaporate, leaving an unstable explosive. Development of cordite. A United Kingdom government committee, known as the Explosives Committee, chaired by Sir Frederick Abel, monitored foreign developments in explosives and obtained samples of powder B and ballastite. Neither of these smokeless powders was recommended for adoption by the Explosives Committee. Abel, Sir James Dewar and Dr. W. Kellner, who was also on the committee, developed and jointly patented in 1889 a new ballistite-like propellant consisting of 58% nitroglycerine, by weight, 37% guncotton and 5% petroleum jelly. Using acetone as a solvent, it was extruded as spaghetti-like rods initially called cord powder, or the committee's modification of ballistite, but this was swiftly abbreviated to cordite. Cordite began as a double-base propellant. In the 1930s, triple base was developed by including a substantial proportion of nitroguanidine. Triple-based propellant reduced the disadvantages of double-base propellant, its relatively high temperature and significant flash, by combining two high explosives, nitrocellulose and nitroglycerine. Imperial Chemical Industries' World War II double-base AN formulation also had a much lower temperature, but it lacked the flash reduction properties of N and NQ triple-base propellants. Whilst cordite is classified as an explosive, it is not employed as a high explosive. It is designed to deflagrate, or burn, to produce high-pressure gases. Nobel and Abel patent dispute. Alfred Bernhard Nobel sued Abel and Dewar over an alleged patent infringement. His patent specified that the nitrocellulose should be of the well-known soluble kind. After losing the case, it went to the Court of Appeal. This dispute eventually reached the House of Lords, in 1895, but it was finally lost because the words of the well-known soluble kind in his patent were taken to mean the soluble collodion, and Hunt specifically excluded the insoluble guncotton. The ambiguous phrase was soluble nitrocellulose. Soluble nitrocellulose was known as collodion and was soluble in alcohol. It was employed mainly for medical and photographic use. In contrast, insoluble, in alcohol, nitrocellulose was known as guncotton and was used as an explosive. Nobel's patent refers to the production of celluloid using camphor and soluble nitrocellulose. And this was taken to imply that Nobel was specifically distinguishing between the use of soluble and insoluble nitrocellulose. For a forensic analysis of the case, see the History of Explosives Vol. 2. The case for cordite, John Williams, Cordite Formulations. It was quickly discovered that the rate of burning could be varied by altering the surface area of the cordite. Narrow rods were used in small arms and were relatively fast-burning, while thicker rods would burn more slowly and were used for longer barrels, such as those used in artillery and naval guns. Cordite and Cordite MD, the original Abel-Dewar formulation, was soon superseded, as it caused excessive gun barrel erosion. It has since become known as Cordite MKI. The composition of cordite was changed to 65% guncotton and 30% nitroglycerine shortly after the end of the Second Boer War. This was known as Cordite MD. Cordite MD cartridges typically weighed approximately 15% more than the Cordite MKI cartridges they replaced, to achieve the same muzzle velocity, due to the inherently less powerful nature of Cordite MD. Cordite Rdb. During World War I, acetone was in short supply in Great Britain, and a new experimental form was developed for use by the Royal Navy. This was Cordite Rdb, which was 52% collodion, 42% nitroglycerine and 6% petroleum jelly. It was produced at HM Factory, Gretna, and the Royal Navy Cordite Factory, Halton Heath. Acetone for the cordite industry during late World War I was eventually produced through the efforts of Dr. Chaim Weizmann, considered to be the father of industrial fermentation. While a lecturer at Manchester University, Weizmann discovered how to use bacterial fermentation to produce large quantities of many desired substances. He used the bacterium Clostridium acetobutylicum to produce acetone. Weizmann transferred the rights to the manufacture of acetone to the Commercial Solvents Corporation in exchange for royalties. After the shell crisis of 1915 during World War I, he was director of the British Admiralty Laboratories from 1916 until 1919. Cordite Rdb was later found to become unstable if stored too long. Cordite SC. Research on solvent-free Cordite Rdb continued primarily on the addition of stabilizers, which led to the type commonly used in World War II as the main naval propellant. In Great Britain this was known as Cordite SC. Cordite SC was produced in different shapes and sizes, so the particular geometry of Cordite SC was indicated by the use of letters or numbers, or both, after the SC. For example, SC followed by a number was rod-shaped cord, with the number representing the diameter in thousandths of an inch. SCT followed by two sets of numbers indicate a tubular propellant, with the numbers representing the two diameters in thousandths. 2-inch and 3-inch diameter, rocket Cordite SC charges were developed in great secrecy before World War II for anti-aircraft purposes, the so-called Z batteries, using unrotated projectiles. Great Britain changed to metric units in the 1960s, so there was a discontinuity in the propellant geometry numbering system. Cordite N, an important development during World War II was the addition of another explosive, nitroguanidine, to the mixture to form triple-base propellant or Cordite N and NQ. The formulations were slightly different for artillery and naval use. This solved two problems with the large naval guns of the day as fitted to capital ships. It was also used in limited amounts with 25 PR and 5.5-inch artillery. Nitroguanidine produces large amounts of nitrogen when heated, which had the benefit of reducing the muzzle flash, and its lower burning temperature greatly reduced the erosion of the gun barrel. After World War II, production of double-based propellants generally ended. Triple-based propellants, N and NQ, were the only ones used in new ammunition designs, such as the cartridges for 105 mm field and for 155 mm FH-70. Cordite charge design. Cordite manufacture, UK government factories. In Great Britain, Cordite was developed for military use at the Royal Arsenal by Abel, Dewar and Kelmer, Woolwich, and produced at the Waltham Abbey Royal Gunpowder Mills from 1889 onwards. At the start of World War I, Cordite was in production at Waltham Abbey Royal Gunpowder Mills and by 7 other suppliers. Existing factories were expanded and new ones built, notably by Nobel's at Ardea, HM Factory, Gretna, which straddled the Scotland-England border at Gretna, and the Royal Navy Cordite Factory, Halton Heath. A factory was also established by the Indian government at Nilgris. Both the Gretna and the Halton Heath Cordite factories closed at the end of World War I. By the start of World War II, Halton Heath had reopened, and an additional factory for the Royal Navy, the Royal Navy Propellant Factory, Caerwent, opened at Caerwent in Wales. A very large Royal Ordnance Factory, ROF by Sopton, was opened in Scotland to manufacture cordite for the British Army and the Royal Air Force. A new cordite factory at Waltham Abbey and 2 additional ROF Ranskill and ROF Riegshammer were also opened. Cordite produced in these factories was sent to filling factories for filling into ammunition. MOS agency factories and ICI Nobel. In World War II, the British government set up additional cordite factories, not under Royal Ordnance Factory control but as agency factories run on behalf of the Ministry of Supply. The company of ICI Nobel, at Ardea, was asked in 1939 to construct and operate 6 factories in southern Scotland. 4 of these 6 were involved in cordite or firearm propellant manufacture. The works at MOS Drumguns produced gun cotton that was converted to cordite at MOS Dalbeattie and at MOS Powfoot. A smaller site at Girvan, South Ayrshire, now occupied by Grant's Distillery, produced cordite and TNT. The ICI Ardea site also had a mothballed World War I government-owned cordite factory. 35% of British cordite produced between 1942 and 1945 came from Ardea and these agency factories. ICI ran a similar works at Deer Park near Melbourne in Australia and in South Africa. Overseas supplies, additional sources of propellant were also sought from the British Commonwealth in both World War I and World War II. Canada, South Africa and Australia had ICI-owned factories that, in particular, supplied large quantities of cordite. World War I Canadian Explosives Limited was formed in 1910 to produce rifle cordite, at its Beloeil factory, for the Quebec Arsenal. By November 1915 production had been expanded to produce 350,000 lb of cordite per month for the Imperial Munitions Board. The Imperial Munitions Board set up a number of additional explosives factories in Canada. It built the British Cordite Limited factory at Nobel, Ontario, in 1916/1917, to produce cordite. Production started in mid-1917. Canadian Explosives Limited built an additional cordite factory at Nobel, Ontario. Work started in February 1918 and was finished on August 24, 1918. It was designed to produce 1,500,000 lb of cordite per month. Factories, specifically a Rdb and a were important for the provision of munitions. Cordite factories typically employed women who put their lives at risk as they packed the shells. World War II, the United States did not use cordite, however, several ammunition filling factories were set up in Canada in World War II to fill American propellant supplied by the USA under Lend-Lease. India and Australia were also approached. Production quantities: large quantities of cordite were manufactured in both World Wars for use by the military. Pre-World War I, prior to World War I, most of the cordite used by the British government was produced in its own factories. Immediately prior to World War I, between 6,000 and 8,000 tons per year of cordite were produced in the United Kingdom by private manufacturers. Between 1,000 and 1,500 tons per year were made by Nobel's Explosives, at Ardea. However, private industry had the capability to produce about 10,000 tons per year, with Ardea able to produce some 3,000 tons of this total. World War I: at the start of World War I, private industry in the UK was asked to produce 16,000 tons of cordite, and all the companies started to expand. Factory, Gretna, the largest propellant factory in the United Kingdom, which opened in 1916, was by 1917 producing 800 tons of Cordite Rdb per week. The Royal Navy had its own factory at Halton Heath. In 1910, Canadian Explosives Limited produced 3,000 lb of rifle cordite per month at its Beloeil factory, for the Quebec Arsenal. By November 1915 production had been expanded to 350,000 lb of cordite per month. The Canadian Explosives Limited cordite factory at Nobel, Ontario was designed to produce 1,500,000 lb of cordite per month. Between wars, factory, Gretna and the Royal Navy Cordite Factory, Halton Heath both closed after the end of the war and the Gretna factory was dismantled. This left the Waltham Abbey and Ardea factories in production. Uses in popular culture. In honour of the military uses of cordite, the Royal Military College of Canada's Mechanical Engineering Department built a ship for use in thermodynamic research, and named it MV Cordite. In the Wasp factory by Ian Banks, a large quantity of cordite resides under the house of the protagonist, Frank. Notes. References. External links: http nigelf.tripod.com/ammo.htm propellant, http cdncucreduktank A = D and D = SN 19170602.2.77